Now let's summarize the video. So it's all about the law of acceleration, which states that when a net force acts on the body, it will be accelerated in the direction of the net force. The acceleration is directly proportional to the force and inversely proportional to the mass of the body. Mathematically, it expressed in this formula. So we have here acceleration, and it is directly proportional to the net force, and it is inversely proportional to the mass. Okay, hopefully you know how to read this formula, and then you simplify it. Okay, so you cross multiply and you get this. So what do I mean by the acceleration is directly proportional to the force? So it means that if the object has a large net force, then it will have large acceleration. So let's say, for example, if this truck has a powerful engine, okay, and this engine would create a large force, therefore it will accelerate fast, right? It would have a greater acceleration. And if it has a small force, then small acceleration. So for example, with the same truck, but it has a less powerful engine, okay? And when you step the accelerator, it would have a smaller acceleration. And then what do I mean by the acceleration is inversely proportional to the mass of the body? So with the same engine, for example, with these cars here, so for example, they have the same engine, okay? This car here has a large mass, and then it would have smaller acceleration. And with the same engine, with this car here, this car would have a larger acceleration. So when we say law of acceleration, it means that if the object experiences an unbalanced forces, okay, if it is initially at rest, then it will start moving, okay? And if the object, okay, is in motion, meaning nagdagan na siya daan, okay, then these three things will happen. It either will change its speed or change in direction or both. Okay, so that's it. So let's have this situation here. A rightward force is applied to a book in order to move it across a desk with a rightward acceleration. Now, let's try to make a free body diagram out from this situation. So we have here the box representing the book, and then yes, it has a wave. And then why is it this book's not falling down? Because it has a normal force that would counter this weight, and then there is an applied force. Okay, and then remember that this book is accelerating rightward. Okay, so this book starts moving, and once it moves, there will be friction. So we have to put friction here. But why is it that the length of the applied force is much longer than the friction force? It is because of the statement. There is a rightward acceleration. There is now an unbalanced forces in the horizontal direction. Okay, so in the vertical direction, is there an unbalanced force? No, because then the weight and the normal force is balanced. They have the same length but in opposite direction. That's why in this area it's not accelerating, it's not moving up, it's not moving down. Okay, and it's not accelerating. And then how about for the horizontal direction? Yes, there is now an introduction of unbalanced forces because the applied force is much longer than the friction force. So this one is much longer than this one. So you would expect that this object would accelerate rightward. Why? Because of the law of acceleration that it states that if the forces are unbalanced, object at rest, just like this book here, okay, will start moving. Okay, therefore its acceleration will be no longer zero, but it will have some value. So, okay, oopsie. Okay, it moves from this side. Next, the slither has reached the bottom of a hill and is coasting to the right while slowing down along the loosely packed snow. You have to ignore the air resistance. So what we're gonna do, we will have the free body diagram. So this will be the slither, and then yes, it has a weight. By the way, that's a slither, and then yes, it has a weight, and then it has a normal force. Okay, and then okay, do we have applied force here? No, because it's just moving. Okay, but it has a friction. Okay, so what do we mean by this free body diagram? Okay, so remember friction, it will always resist the motion. If the motion is going here, then the friction would be in the different direction, just like this. Okay, so in the vertical direction, the forces are balanced, but in the horizontal direction, okay, this will be the unbalanced forces, okay, or force because it's only one. Okay, so we have here the friction force, and we all know that if the forces or if the force are unbalanced, okay, if the object is in motion, meaning it's running, okay, it's running, okay, it will change its speed, or it will change its direction, or both. Okay, in this case, since in the horizontal only the friction is present, so it will change its speed. Okay, it will change its speed, and it would decelerate. What do you mean by decelerate? Okay, it would slow down. It would slow down. So meaning, while the slither is moving in the rightward direction, it will slow down because of the friction, and eventually it will stop. Mhm. Now, here's the application of the second law of motion. Two blocks of masses. We're gonna call the first mass M1, which has a mass of 4.5 kilogram, and M2, which is a mass of 6.5 kilogram, resting on a frictionless surface, mhm, are connected by a light and extensible cord, as shown in the figure below. A horizontal force of 33 Newton directed to the right is applied to the block with M1 as shown. So you have to create a free body diagram, you have to find the acceleration of the masses and the tension in the cord. This one. So let's start with the free body diagram. So I think it'd be simpler if we start here with mass 2. Okay. So for mass 2, it has a weight. Okay. Okay, it has a weight going downward, and there must be something that would counteract this weight so that it won't fall down. So it has a normal force because it's in contact with a surface. Okay, and then notice that there is an inextensible cord here. So, and this cord provides a tension force. Hmm. Do we have friction here on the left side? No, because it is resting on a frictionless surface. So, no. So we are done with the free body diagram of mass 2. Now let's go to mass 1. For mass 1, yes, it still has a weight. okay, going downward, and there is a force perpendicular to the surface. That's the normal force, and they have the same length, meaning the same magnitude, but in opposite direction. And then there is a horizontal force going to the right. And then here there is an inextensible cord that provides the tension force. Okay. Notice that the horizontal force is much longer than the tension force. Why did I do this? It is because this block here is accelerating. So there is an unbalanced force in this area, and we could assume that because the horizontal force is much larger than the tension force, then we move rightward. Mhm. So we are done with the free body diagram. Let's go to letter V. You have to find the acceleration of the masses. Hmm. So we have here the free body diagrams. Mhm. So we'll find out if there is an acceleration in the vertical direction. So let's have for mass 2. So why is it that the summation of the forces in the vertical acceleration, I put it 0? Because in the free body diagram, the weight 2 and normal force is equal. So it's the M2 is not going forward, it's not going upward, it's not going downward. So we could assume that the summation of the forces in the y direction is 0. Okay. Next would be you have to find what would be the formula in getting this um, uh, summation of the vertical forces. So add all the upward forces and then subtract all the downward forces. So we have it here. F normal force is positive. Subtract it with the forces going downward, which is weight 2. Then, as a result, that will be summation of Fy. Okay? And then, uh, simplify this one. Okay, you have this. So, because the value of the uh, summation of forces in the y direction is 0. And then, so, simplify it more. You transfer it here. And it sounds like this. So then the minus W2, once you transfer it to the other side, it becomes positive. So we have now this equation that we could have, understanding that the normal force is equal to the value of the weight. But what is the weight? Do we have the value of the weight here? Shall we write 6.5 kilogram for the weight? Hmm. The answer is no, it's not 6.5 kilogram. Okay, here's the formula in finding the weight. We have the mass 2 multiplied by the gravitational acceleration. So do we have the value of mass 2 here? Yes, we have here 6.5 kilogram. Do we have the value of the gravitational acceleration? Yes, we all know this one. This is our friend. This is 9.2 meter per second squared. So you just simply substitute here, and then you multiply, get your calculator, and then 6.5 times 9.8, you get this number, 63.7. And yes, okay, you may add zeros so that we would comply our agreement that your final answer must have at least 2 decimal place. And why is it Newton? Because when you combine these units here, okay, when you combine these units, it becomes Newton. But we're looking for what's the value of the normal force. We have this equation now. We have this equation. Oopsie. Oopsie. Here. So, mhm. So we have here, you just simply substitute the value of the weight here. So the value of the weight here is 63.7 Newton, and here is 63.7 Newton, but they are in opposite direction. Mhm. So when you add this to positive 63.7 plus negative 63.7, because it's going downward, the answer is 0. So if this one, in this case, in this area here, okay, it experiences a balance force. So it will not move upward, or it will not accelerate upward, or it will not accelerate downward, because this one is a balance force. Next would be in mass 1. Same thing here. The weight and the normal force is equal, so we could assume that the summation of the force in the vertical direction is 0. Next would be, you have to find the formula for this summation Fy. So you add all the forces going upward, and you subtract it all the forces going downward. So we have here Fn1, that's positive, minus weight 1 is equals to this one. Then you substitute, okay? This one, the value is 0, okay? And then just like with the other one, you transfer this into here. So it's negative minus weight 1, so it becomes positive. Okay. So, shall we write here the value of weight 1, which is 4.5 kilogram? The answer is no. You must not write 4.5 because we have now the formula for weight. So we have here mass times gravitational acceleration. What's the mass 1? We have here 4.5 kilogram times 9.8 meter per second squared. And then you do your math here, and it will have 4.4, 44.1 Newton. Okay, let's check. Oopsie, here. So, 4.5 times 9.8. Oops. Uy, what am I doing? What am I doing here? Okay, here. 4.5 times 9.8, and then yes, you got 34.1 Newton. And then you just simply substitute this one, and then you have the value here. So the value for this one is 44.1 Newton. Is here the same, 44.1 Newton. Well and good, but they are in opposite direction. That's why the summation is 0. Okay, well and good. Now let's go to this one. Find the acceleration of the masses in the horizontal direction. So first, okay, since this we're looking for the acceleration, we have to go back to the second law of motion. Okay, so we have here the net force is equals to mass times acceleration, and then you simplify it so that you will get the formula of the acceleration. So how to get rid of this mass? You just simply divide both sides by mass, cancel it out, and it would be this one. Oopsie, I'll fix this. Okay, so you have here acceleration is equals to net force times mass. Now, so here in the horizontal direction, the net force, or the F net, is equals to the tension force, because there are no other forces acting in this side. But, okay, we don't know yet the value of the tension force. So we cannot use this. How about here? So the net force here is F net would be, okay, the F here, the applied force, which is positive, minus the tension force. But we don't know yet the tension force, so we cannot use this one. So the solution for this is we will apply the second law of motion to the entire system. Mhm. The thing is, this would be now, if this is the entire system, okay, this is the entire system, and this would be now the net force. Okay, let me use another, this is the entire system, okay, I'll use another color. So this one would be the entire net force. And do we have the value of this one? Yes, and that's 33 Newton. Mhm. So F net here would be 33 Newton. Okay, and then because it will be no longer mass 1, it will no longer mass 2, but we will have the entire system. This mass 1 and mass 2 will be the entire system. So we have to add all their masses. Mhm. So here we will have F net, which is 33 Newton, okay, and mass 1, which is 4.5 kilogram, plus mass 2, which is 6.5 kilogram. And then get your calculator. I have it here. And then 4.5 plus 6.5, that would be 11. So 33 divided by 11, that would be 3. Okay, meter per second, and that's going to the right. Okay, because the net force here, this is the entire system, the net force is going in this direction. You may write like this, 3.0 uh, meter per second squared. Instead of writing right, you may also choose and writing this, positive 3.0 meter per second. It's just the same. Now let's go to the tension in the cord. Okay, so you can solve this problem using this free body diagram here or in this free body diagram here. So let's have first this one. Okay, so notice in the horizontal direction, only this one is the existing force, okay, in the horizontal direction. So we could assume that the net force in the horizontal direction is equals to the value of the tension force here. So this will be our question number 1. Next would be, we all know that we have the value of the acceleration. So we'd summon the formula for the law of acceleration, which is the net force is equals to the mass times acceleration. So this will be our equation number 2. But we are looking for the tension force. We are looking for the tension force here. So let's substitute this F net into this T. So here, so instead of writing F net, okay, or the net force, okay, we will have the tension force because they are equal. Oops, see. So this one. And then mass. Mass that we are referring to is mass 2 because this is the free body diagram of mass 2. Okay, and then the acceleration. So we have now the formula of the tension force. So question, do we have the value of mass 2? Yes, we have here 6.5 kilogram. Do we have the value for acceleration? Okay. Yes, because we solved it a while ago. The entire system will have an acceleration of 3.0 meter per second squared to the right. Okay. So whatever the acceleration of the mass 2 will also be the acceleration of the mass 1 because they are connected by this inextensible cord. So yes. So here 6.5 times 3. Okay. So let's summon our calculator here. Times 3, and you get this 19.5 newtons. So kilogram, when you combine kilogram times meter per second squared, it becomes newton. So that's the first way to solve this problem using this free body diagram. Next would be this. Okay, this is an interesting one. So we have here the applied force and the tension force in the horizontal direction of this free body diagram. So we could assume that the net force is equals to the F, and it's positive because it's going to the right, and minus, minus the tension force, and it's going to the left. That's why you have to subtract it. Okay, and then you get this first equation. F net is equals to force, applied force minus tension. And then since we know already that this one involves the law of acceleration, so let's summon that formula. So F net is equals to mass times acceleration. And then in this situation alone, we all know that F net here is equals to 4 applied force minus tension force. So we will break this down, we will substitute it. So that's why it becomes like this. Okay, remember? Okay. Okay. So F minus T is equals to MA. Okay. And then you simplify. So we want the formula of the tension force. So this one is positive, the applied force. And then you put it here. Okay. So it becomes like this. Okay, so it becomes minus F because here it's plus F. So once you transfer it, it's become minus F. And then, okay, you have this formula now. Okay, you can simplify it further or you may go to substitution. It's all up to you. Question, do you have the mass? And we're referring to mass 1. Do you have the value of the mass 1? Yes, and that's 0. I mean, not 0, that's 4.5 kilogram. Do we have the value of acceleration? Yes, we have the value of the acceleration because whatever the value of m2 will also be the value of m1 and vice versa. And we solved it in the previous problem, and that's 3.0 meter per second squared. Do we have the value of the applied force? Yes, we have the value of the applied force, and this is 33.0 Newton. That's the 33.0 Newton. So well and good. So let's substitute. So 4.5, that's the value of mass 1, okay, times 3 meter per second squared, that's the value of the acceleration. We already solved this one in the previous problem, minus 33.0 Newton because this is the value of the applied force. So simplify, you multiply this two, it becomes 13.5 Newton minus 33 Newton. Okay, and then you simplify it further, it becomes negative 19.5. And then remember there's a negative here, so simplify it further. Okay, here. So divide both sides by negative, and you get this one. So notice whatever your way in solving, if you're going to use this free body diagram here or you're going to use this free body diagram here, the answer is still the same. The answer is still the same.